I guess. Okay, so I'm recording now. Okay, so um, what I wanted to do was to go through the five easier problems on the North American qualifier last week, and then I guess the three hard problems that nobody got from our university. Probably there's not much of a reason to go over it in this forum, but maybe our team one, if we want to talk about them, we can separately talk about them. Um, so I guess from now till March 6th, we will continue doing some practices. But maybe I will do. So what my plan now is to separate the practice a little bit. I was thinking that team one, I would try to maybe give them some more directed focus things to look at, and the rest I will give maybe more general. But possibly I would look, since I think most of you haven't even seen the previous regionals of this region. I would perhaps go start looking at some of the regionals from previous years, and then we can go through some of the, I would say, easy to medium problems. Because if you do well in those, if you are confident and get them correctly quickly, those usually don't require a lot of special knowledge, just I guess accuracy in reading the problem statement, accuracy in implementing the solution. If you can do that, then you would probably be in the middle third and maybe even top half just by doing those problems quickly and correctly. Okay, and then if you're just starting out, I don't think you should be aiming for top 10 right away, but even middle third is a good showing for the first time. So I think that's what I would be doing. So at the end of this, I will tell you what problems I have to look at next time, and then the team one, I guess I started this out of Discord chat group, and I guess we can talk about that in that separately. Um, okay, so let's do a share screen. Okay, so here we are. This is the scoreboard from last Thursday night. Right, so there are three problems that are easy, right? C, D, and F. Now, even though they're easy, there's a difference between, you see that our team, okay, well, we'll forget about the fact that these guys failed the first time, but they got it at 28 minutes, 43, and 35 minutes, right? There's a big gap between our second team, for example, right? Not that I'm picking on you guys, but it's true, right? There's six, almost 60 minutes, 62 minutes, plus two penalties. So that's 100 minutes here. This one is the same because every wrong submission is 20-minute penalty. So this is 40 minutes plus another penalty. So that's 60 minutes. And that's 120 minutes plus another four penalties. So there's difference between just on the first three problems. It's pretty big, right? And I just want to show you what some of our top competitors in this region. At U of A, I don't know exactly who these people are. This is the team one, and they solved six problems at the end. And the last problem that they solved was almost at the end with 12 minutes to go, and it took them 4 tries to get it. And they were kind of stupid and misread the problem, so that's why it took them 6 tries to do this. Although if they read the problem right, they probably could have done it pretty quickly. And you see that the time difference, right? You see that they got 7 minutes here, 9 minutes they got the other one, and so on. And then which other one is that? This is another top school from our region, University of Utah. They also did 5 problems. They did it a little bit slower than our team, and they couldn't do B, E, or G. So B and G, there's a huge step up compared to the other 3. So C, D, and F are clearly easy in the set. A and H are a little bit harder, but I think they are definitely approachable if you have a little bit more knowledge, especially H. A is requires some special knowledge that you may or may not have, but after I tell you today, you will have that knowledge, hopefully. So overall, if you look at this here, Clearly, Simon says it's the easiest. 364 correct. 344 correct for flexible spaces. 8 queens, it's a mixed popular one, but you also have to notice that, like many of you, you failed the first time. I think maybe all of you, because there's one tiny but tricky case that maybe you didn't think about. So even though lots of teams solved it eventually, it was not as successful as the other one. And then Cantina and using digits each have about 100 and some, 130, 160. And then there's a huge drop off, right? This is 48 and the other ones only have 19 and 15 correct submissions. So anyway, let's, so what I want to say is for the easy ones, right? D, F, and C, the goal is not to solve it. I mean, of course you want to solve it, but the goal is to solve it as quickly as you can and correctly, okay? And because there's a 20-minute penalty for each incorrect submission, it's better if you slow down slightly just to make sure that you don't pay that 20-minute penalty by making sure that your submission is correct. Okay, so now let's see. Okay, I don't think I have to read the problem again because you have done the problem. So basically it says that you have n up to 1,000, and then each of the lines, n lines is one command, at most 100 characters. You have a sequence of one or more words, only lowercase and uppercase letters A to Z, followed by a period. Some commands begin with Simon says, others may not. The phrase Simon says only occurs at the beginning of a command. If a command begins with Simon says, there's another space and at least one additional word after says. No lines contain leading or trailing spaces. For each line that begins precisely with Simon says, output the rest of the line. Each line does not begin with precisely Simon says should be ignored. Okay? It says the rest of the line, and there was a question during the contest. Does that mean this space as well? And the answer is yes. But if you don't know for sure, you can hit copy, or you can just try to highlight this, and you can see that extra space. Also, you can click on this, and you can download the sample file, sample input output. All the problems on Caddis will allow you to do this, and then you can see that there's a space. Okay, and my advice is that you should download the sample data instead of typing this in yourself or quick copy and paste, and just run it and diff it. Okay, so how do you run it? If you have a program that you have compiled called program, then you would say program less than, and then the input file. Okay, so that will redirect the input as if you're typing the content in the file. Then vertical pipe diff minus the output file that's supplied. So the input file, these are the sample input output file that they supply. And this says that take the outputs of this program, use that as the first argument. The minus means take it from the pipe, take it from standard input actually, and then diff it against the outputs. And if there's no outputs, no news is good news. Diff will produce nothing if there's no difference. And if there's any difference, if diff produce anything at all, then you know that your output doesn't match exactly. And then you have to go and look why. Okay. So that's how you can make sure that your whatever you're trying to do matches exactly. Okay, because that was a question during the contest, whether there was a space or there was no space, right? Okay. So really there's not much to say, but the question is how do you do this quickly or easily? So the first thing to realize, I guess, is that these are lines, right? So that you have a bunch of lines. So it's easiest if you do line-oriented inputs. So if you try to use something like C in arrow, arrow A, where A is a string, like this, then every time you do this, it skips all the spaces, and you might be in trouble. Okay, so we generally don't want to do this if you have to worry about preserving spaces. So what we do is instead use getLine. So S being a string. So this will get a line, get something into a string from the current position of the input all the way to the end of the line. And so you might say, well, okay, C in N, and then you might say for I equal to 0, I less than N, I plus plus, do this. Okay, and if you do this, you'll be in trouble because what happened is it will read N, so here it reads N, but you actually haven't gone to the next line yet. When you read this, it will read until the character that's no longer an integer, and there's a hidden character, which is a new line at the end. So your cursor is kind of stuck right here. And the first time you get line, it will read everything until the end of the line. So we'll read this part, move on to here, and it will give you an empty string because you read this as the first line. So typically, if you have get C in like this, using this kind of operator to read input, and then after that you want to read one line at a time, there are many ways you can do this, but I usually just do this once to get rid of this new line. So you move down to here, and then you will be able to read these 3 lines. Okay, so that's the one first thing that's, I guess if you're familiar with how getLine works and how it interact with other things, then you can make sure you do. Second thing is how do you decide, how do you pick the string apart? How do you know if there's Simon says? So the easiest thing to do, Simon find s.find Simon says, and that will return an index of the first occurrence, or so either an index of first occurrence, oops, okay, first occurrence, or it will return a special constant, which is this, if it's not found. Okay, and this is, let's pretend that it's -1. I'll put double quote in here because it might not be -1, but some kind of invalid index. So what you can do is you just say if s.find this is equals to 0, right? That means that your sentence begins with Simon says, otherwise it didn't. And then how do you find the rest of the string? Well, you can use a substring command. Substring commands take 2 parameters. The first parameter is the index of where it starts. And then the second parameter is, I believe, the length. Let me just make sure, because I did string substring. Oh, the length. Okay. You see, I forgot already. It's the length. Oh, actually, I wrote length. Okay. So you can work that out. I suppose you can work out how long it is, but you can also figure out pretty quickly what is the index because you know exactly how long this string is. Simon says is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, you know, you can write the index of this 4, 5, 6, 7, 8, 9. So the rest of the string start at 10. And I suppose if you really want to, you can figure out this by saying the length of the string minus 10. But you don't need to, because the default parameter actually just go all the way to the end of the string. So all you have to do is call this and then print it out. Okay, maybe I'm spending a bit more time than I should on this problem, but anyway. Oh, I set to, why do I use 11? Okay, let me see. Let me blow this up a bit. This is the solution that is accepted. Okay, so far this is pretty much what I told you. Read and, let me blow it up a little bit more. Read and, then eat the line. Then for each one, I read a line. I ask if Simon says it's equal to, if it's true, then it starts at 11. Why did I start 11? Let me see. 1, 0, 1, 2, 3, 4,
11 is the
5,
space, right?
8, 9, 10. Oh, so
And we need that.
So I actually skipped the space the way that I did it. So maybe it didn't matter. I don't know. Maybe it didn't even matter whether there's a space or not because this was accepted. Maybe I was cheating because I knew that Caddis usually doesn't care about spaces. It used to be in the many years ago, this would return what they call presentation error, which means that your answers are correct except spaces and linear lines. But there's no such thing anymore. This will just be accepted. So maybe if you thought you were failing because of the space, maybe that wasn't the problem. Maybe there was something else that you fixed. Well, okay, let me edit and resubmit. Oh, oh well, I was going to change it. Okay, so if I were to say 10 and then submit, let's just see if that would still be accepted. Where is it? Okay, have to wait. Is it judging? It's judging. So it's still accepted. So I guess, yeah, it doesn't, I guess it didn't really matter the spacing. So generally on Caddis, unless they specifically say that spacing matters, the answer is it doesn't. So from a problem setter point of view, I know how to actually submit problems and configure it from Caddis. If you want exact match and then not ignore extra space and so on, you actually have to specify extra settings. The defaults will just ignore spaces if there are any differences. So anyway, that's what it is. Okay, so that's that. There's not a lot to say. Any questions? Okay, this other one. Okay, so 8 queens, right? So what did I say? I think I told Jana that I looked at her code and there are some suggestions that I was going to make. So let me explain what the problem is. I think all of you have read it, but the idea is that you're given an 8x8 board. Dots means that nothing is there. Star means that there's a queen, and you need to tell me if this is a valid 8-queen solution. 8-queen solution means that, okay, so you have to read this carefully. In the 8 queens puzzle, 8 queens must be placed on a standard 8x8 chessboard so that no queen can attack each other. 2 queens can attack each other diagonally in the same row and same column here. Okay, so many of you did not read this sentence carefully, right? 8 queens must be placed. So many of you go and do the hard part and say, make sure that no queens can attack each other, but then you didn't actually check that there are 8 queens, right? So that was the one thing that many people missed. But then the question is, how do you actually check the queens, right? So there are many ways you can do this. So what should I do? Should I attempt a whiteboard? Okay, so one way to do this is to say, well, just loop until you find a queen. Okay, so you found a queen. It's found. Okay, so wherever it is, you found a queen here, and it's row R, column C. Okay, so now what are you going to do? You're going to write 8 loop possibly. You're going to write one loop to go up. You're going to write one loop to go left, well, left, right, down, and then the 4 diagonal. Right, and then see if you hit any other queen. And if you don't, then you're good. Otherwise, you're not good. So how do you go up, right? So maybe you write something like for, I don't know, int R2 is equals to R minus 1. R2 it's greater than or equal to 0. R2 minus minus, and then you write check R2 and C. Okay, check just means see if that thing is that cell has a queen, and then maybe you do something else. Maybe you say for int. Maybe what about this one, right? Then you have to be careful. You have to say R2 is equal to R minus 1, and then C2 is equal to C plus 1. And then you have to remember R2 is greater than or equal to 0 and C2 is less than 8. And then you have to say R2 is minus minus, and then C2 is plus plus, and so on and so forth. And then you write 8 of these loops, and then you have to be careful for each direction. Where do you start, which direction you're incrementing, and what you have to check. And it's going to be really easy to mess up. Right? This is kind of how you did it, Jana? Is that what you did?
Yeah, I did like a 2-dimensional array and just crossed out any of the points that were
Right.
covered by that queen. And then if I found one that was in one of those spots that were crossed out,
Okay.
it
Yeah.
was invalid.
So what you did is instead of for each queen check whether there's another queen, for each queen that you place, you kind of say these are all the places that you can no longer use. And then if you later on you see a queen that's in one of those forbidden places, you say no. Right?
Yeah, that's what I did.
Okay, Josh, your team, who did that problem?
I did.
And did you do this? I hope not. Did you do what I just said?
No. Wait, do you want me to say what I did?
Was it linear time or was it constant time?
For every queen?
For each queen.
It should be constant, I think.
Good. Okay, good. Okay.
Maybe not. I don't know.
Okay, well, okay, I'll keep on going then. All right, so now the one thing that I want to say, this is something for the new people. Instead of writing 8 different for loops for each 8 directions, it is easier if you actually write, I guess if you're in a normal class, they will tell you to write cons, but I don't like typing more letters than needed, so I won't do that. And we'll write an array of 8 things. So what do I mean by that? So I will just label these directions 0 to 7. And I say, okay, for direction 0, every time I move, row gets decreased by 1. Same thing with direction 1. Direction 2, row doesn't change. 3, 4, and 5, direction increased by 1, 0, and minus 1. Okay, so if I were to say, look at whatever direction it is, how does the row index change every time I move? Similarly, I can say, well, how does the column index change for every direction? If I'm moving up, the column doesn't change. If I'm moving at directions 1, 2, and 3, every step to change it by 1. 4, no change, and then the other ones are minus 1. Okay, and why is that useful? Because what I can do now is I can say for the direction from 0 to 7, I can say something like this. So int R2 is equal to R plus DRD and C plus DCD. And then I can say while, or for, doesn't matter if it's while or for the, well, I guess I should use for, just so that. So, well, I guess the for the initialization is actually here. So I'll just say for this. And then I have some function that say if R2 and C2 is in bound. So you just write something that checks, 0 is between R2 is less than 8 and 0 and C2 is less than 8. So you can write a function that checks that. And then the increment is just R2 plus equals DRD, C2 plus equals DCD. And then inside you can do something with R2 and C2. So what's going on here? What's going on here is that I encoded all 8 directions with this table here. And then whichever direction I go, I just look up the offset of the appropriate entry in the table. And once I know the offset, I don't have to write 8 different loops to do the same thing. And it's a way for me to simplify my code. As long as I get this table right, it's much easier to get this part right? And this is sometimes what we call table-driven code. You write a table to simplify your logic, okay? So this is a different way of doing it. It's a slightly different way, but the idea is the same as before. For each queen, you kind of go to all 8 directions, either because you're trying to see if there's another queen, or if you're trying to mark off squares that you can no longer use. Okay. But that's not the best way. Okay, so what is the best way? The fastest way. I see a queen here at row 4. Okay, let's just say row 4. I don't even care about columns or, well, okay, let's make a column. Okay, so what do I know? I know that no other queen can be in row 4 and column 3. The diagonals I have to worry about, but let's not worry about those for now. If I have a Boolean array, let's say row used, which rows have been used, and 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. I guess I would just mark this as true, the rest are marked to false. And then every time I see another queen, row 5, I can mark this to true. And then maybe I see another queen, row 4, and then I try to mark true, and I realize that, no, I have already marked it to be true. So what am I doing? I'm basically saying, for each row, have I seen a queen or not? And if I have, then I know that I'm done. I know that that's no good. And it's really easy, right? You just have an array. You can check that. And basically, this is kind of the idea of, if you're scanning, if you see a queen and you're scanning this way on the same row, have you seen another queen? Well, you're just remembering this row if you have seen the queen. You can do the same thing with column. You can do the same thing with column. Right, column 3 is now true, and then column, I don't know, 6 is true. And then you have another queen, 1 is true. And then if you have another queen in column 3, now you try to hit this, and now you know that it's already used. So that's an idea. But the problem, of course, is this will only take care of these 2 directions. You still have to worry about this direction and this direction. Okay, so what to do? Well, if you look carefully at the coordinates, okay, I'm just going to draw 4 because I don't want to, it's hard for me to draw everything, too many. Okay, so I'll just do this. but even if you have more, it's the same. If you look at this diagonal, what do you know? That the row and column are the same. If you look at this diagonal, you see that row plus 1 is equals to column, right? Row plus 1 is column, row plus 2, 1 plus 1 is 2, 2 plus 1 is 3, etc. And this column is row plus 2 is column. What about this one? Well, this is row minus 1 is column, and so on. Another way to see this is that row minus column, it's a constant. Oh, did I? Hang on. Okay, actually, I got the sign mixed up. Okay, but anyway, the whole point is that the row minus column is a constant. That's the important thing. And how many diagonals are there in this case? There are actually, so row minus column can be anywhere between +3 to -3. So there's 7 diagonals. In the case of 8 by 8, there are actually 17 diagonals, right? No, wait, sorry. Hang on. What am I doing? It's between 8 and -8. Yeah, 17 diagonals. So what you can do is you can have an array that's indexed by, let's say, 0, 1, 2, up to 17. And if you were to just take the coordinate of the queen and say, what is r minus c plus 8, that will shift -8 to 8 to 0 to 16. So 0 to 16, sorry. And each of these, if they're on the same diagonal, it will be mapped into the same number. And so now you can use the same trick. For each, if you have a queen here, you can then say, okay, r minus c plus 8, it's r minus c is 1 plus 8 is 9. So I go and mark the 9th spot true. And then if there's another queen that's on this diagonal, you will map to here again. And you'll realize that there's another queen here. Okay, so it's the same concept, but it's slightly different, more difficult because of diagonal indexing. Okay, what about the other diagonal? If you look at the other diagonal, so okay, maybe it's easier if I just erase everything. Whoop, what did I just do? I hit a button that shouldn't have. I have a keyboard now. How do I get the key, quit the keyboard? No, did I quit my, oh, I quit my drawing program. Okay, let me try again. Okay, so if I have the other diagonal, again, there are going to be 7 diagonals in the case of 3 by 3, but in the case of 8 by 8, there'll be 17 again. And this time the diagonals are this way. And you'll realize that in each diagonal, r tab plus c is a constant. So this diagonal, r plus c is 0. This diagonal, r plus c is 1, 2, 3. This diagonal, 1 plus 3, 2 plus 2, 3 plus 1 is 4, 5, and 6. So the diagonals, r plus c, it's from 0, 1, 2, up to 6. And in the case of 8 by 8, it will be from 0 to 6, from 0 to 16. So all you have to do then is, again, you would have an array, a Boolean array that's indexed by 0 to 16 to indicate which of these diagonals have been used. And if you have a queen here, this is row 1, column 2. So you go to row 1, column 2, r plus c. It's this one, and you mark it true. And if there's another queen in the same diagonal, it would also have the same sum of row and column. So that's the trick. If you kind of remember which row, which column have been used, but also which of the two types of the diagonals have been used with this clever indexing, then every time you place a queen, you can quickly check the 4 arrays to see if that line has been used, whether it's row, column, or the 2 diagonals. And if any of them have been used, you're done. And if none of them have been used, then you just mark them to be used, and then you move on to the next queen. So, I mean, for this problem, because it's only 8 by 8, it really doesn't matter how fast you do things, right? So what if you have to scan everything in 8 directions? It's not going to take you that much time. If I give you an array if I give you a 1000 by 1000 queens problem, then of course that will be a lot more work scanning. But using this would be constant time still. Okay, it doesn't matter how big your grid is. So that's a trick that I guess I want to show you. It's not completely necessary for this problem, but who knows? It could be useful for a problem in the future. Any questions? Is that how you did it, Josh?
Of course not. I did it the slow way.
You did it slow way. Well, you told me that you think it's constant time. Anyway, it doesn't matter.
I was just saying words, I guess.
Oh, okay. Well, you did say those words in constant time. Okay, so this is that. Flexible space is the next problem, and basically you have this room, a wall or whatever, that's this long, 0 to 10, and you have these positions that you can decide to put a wall. And you can, for each position, you can put a wall or not put a wall, it doesn't matter. And every time you put a wall, you can form spaces. So for example, if you put a wall at 1 and a wall at 4, then you can form a space of length 3. But you can also form a space of length 6 from 4 to 10, and space of length 1 from 0 to 1. And the question is, what are all the different sizes that you can form by putting in 0 or more walls? Right, that's the question. And basically, each possible amount of space can be delimited by a left wall and a right wall. And so you just have to try where are all the left possible walls and where are all the right possible walls. And then you have to say, okay, how big is this room, right? This room is at most 100. And the number of intermediate partition, the number of places that you can put things in, is at most is less than W. So it's at most 100, actually it's most 99. So it's not really that many. So you can in fact just try all possible left and all possible right endpoints and see what the difference is, right? So you have to remember, of course, not just these P locations they give you, but also 0 and W, because those are always there. And then you basically just say, try them all, right? So you can, if you have all the wall locations, so if you have an int, let's just say int wall location, and then there are at most 100 of them. But is that most 100? Let's just make it 101. Why do I say that? Because I want to include, so add 0 and X and W. Well, I shouldn't use W. What should I write? Int, let's say wall 101. So add 0 and W. Whoops. Okay, how do I undo? I'm trying to move something out the way here. Okay, it's better. So I can say move at the 2 outside walls, and then of course add all the P points that they give you to this array. And then you basically just loop through them for I from 0, I less than whatever the number is. So I guess P plus 2, because it's basically the P points plus what I added. For J equal to 0, J less, so I should say I plus 1. So all the pairwise, and then the difference would just be the absolute value of wall I minus wall J, right? And then you have to remember the difference. And the word is remember. So what do I mean by remember? So what do we need to produce? Each partition is at a distinct location, and the partition's location will be listed in increasing order. That actually doesn't really matter. And then your program should output a list from smallest to largest of each distinct width that can be achieved. So you want them sorted, you want them distinct. So there are many things you can do. You can stick them all into a vector. You can sort them. You can remove the duplicates. Or you can stick them into a set, which automatically sort things and remove duplicates. Either way is fine. There's really no right or wrong answer, because there are really only 100 things. So whatever you do is probably fast enough, unless you do something very, very strange. Chances are it'll be way more than what you need. Now, Blake asked the question: is there anything faster than n squared for a larger problem? Is there anything larger than n squared for? So I don't think there is anything larger than better than n squared for a larger problem, because I think we can actually construct a test case where the size of the output, the number of possible answers that you have to print, it's n squared. Okay, so for example, let me see if I can construct this. If so, let's just make it really big. So if C1 here, so if this is 1 and 0, so then of course you can do 1. And now if you have put it at 2, no, sorry, 3, I mean, I want this to be 2. Then I think you can do 2 and 3, of course. And then if you put it at 4, then can you, let's see here, what can you do? Can you do all of them? Then you can do 4, you can do 6, you can do 7, right? And then if you double it again and do 8, then you can do 8, you can do 12, you can do 14, you can do 15. And I think if you keep doubling the next one, so if you make it really large, then you can guarantee that every time you add another one, all of these other ones are distinct. So the output itself, if you were to produce the outputs one by one, you cannot avoid n squared time, because printing the output would be n squared time. So I don't think that there's any way you can make it less than n squared, even if it's larger. If you didn't have to print the output, if you just have to say, tell me how many there are, then I'm not absolutely sure. But I think it's still true that, because you have to keep track of n squared things, I think. But I'm not absolutely sure about that. So it's a good, interesting question, but off the top of my head, I would say you have to do it n squared time, even for larger. Okay, so anyway, and I think the main thing was to realize, to figure out what it is that you're going to do to deal with the output. You have to sort, you have to do a distinct with, right? So like I said, maybe the easiest thing is to use set. So if you use a set, right, set int s, and then in your loop, you would just say s dot insert difference. Oops. I'm trying to figure out that my Zoom window is always covering places that, and I try to move it. I have to remember to switch off my pen. Okay, so insert the difference. And then up, so I have this loop that insert all the difference. I think it was a double for loop. Okay, and then to print everything at the end, you can just say for auto like this, cout space like this. Okay, and then you can print out, I guess, print out a new line at the end. Right, so sets already keeps things sorted and already get rid of duplicates. So that's the important thing about sets. If you were to use a vector, that's fine. So maybe you have vector v, and then in the loop you have, say, v dot push back. My pen is kind of moving in a strange way here. Back diff, and then the problem is that this might have some duplicates. So to remove duplicates, the first thing that you got to do is to sort the array. So that would sort it. And then there's a function called unique, which will somehow get rid of all the duplicate items, except that it kind of does things in a funny way. So what do I mean by that? If you have a vector, let's say that the vector is 1, 2, 2, 3, 3. Okay, so this is your vector. After you call unique, it will be like this. So it is true that you get a vector that has the duplicate removed, but it doesn't delete or resize your vector to get rid of everything. So you still have these two things hanging around. But what unique returns is an iterator pointing to the position just past the end of the unique array. So what you do is you say minus begin of v, and that will, so if you take what is returned from unique and you subtract from it begin of v, that will give you the number of elements that are unique. And then you do v dot resize, and that will resize the array so that it's really containing only the unique elements. And then after that, you can, I guess, print everything the same way. For auto x colon v, cout x with space or something like that. Okay, so unique is a little bit weird because it moves things around and make things kind of unique, but then the empty space, it's not really empty. It's just still there, but it just tells you where the beginning of the empty space is, the return value as an iterator. So when you subtract from begin, it will tell you how many elements there really are, and then you call resize to make it contain only the unique elements. So this is a little bit of a multi-step process. If you have never used this before, it's a little bit weird because you would maybe expect unique to actually resize for you, but it doesn't. Okay, any questions about this? Okay, so this one and the 8 queens and and Simon says those are the 3 easy problems. And I would say that for regional contests, I would expect most teams to solve those 3. And the question is, how long does it take you to solve the 3 eventually, right? That's the issue. Now, the next 2 problems start to get to a little bit more algorithmic thing. Okay, so this one, I will actually read the problem in front of you a little bit more because not everybody have read the problem. Okay, so Cantina Babel. So characters in Star Wars each speak a language, but they typically understand a lot more language that they don't or can't speak. So anyway, there's some example. But anyway, Han Solo might speak in Galactic Basic, and Chewbacca might respond in Sriwivuk, if somebody knows how to pronounce that. Since they each understand the language spoken by the other, they can communicate just fine like this. Okay, so the language that they speak may not be a language they understand. It's a little bit weird. Or I guess they can, maybe they're all, so they can understand some language that they can't speak, and I'm not absolutely sure if they definitely understand the language that they speak themselves. So let's keep reading. So we say that 2 characters can converse if they can exchange messages in both directions. Okay, so both of them understand each other. If they didn't understand each other's language, 2 characters can still converse as long as there's a sequence of characters who could translate for them through a sequence of intermediate languages. So for example, Jabba the Hutt and R2-D2 might be able to converse with some help. Maybe when Jabba spoke in Huttese, Boba Fett could translate to Basic, which R2-D2 understands. And when R2-D2 replies in binary, maybe Luke can translate to Basic, and then Bib Fortuna can translate back to Huttese for Jabba. Okay, and then there's so in Star Wars Episode 4, there's a scene with a lot of different characters, all speaking different languages. Some pairs of characters may not be able to converse, even if others in the cantina are willing to serve as translators. This can lead to all kinds of problems, blah, blah, blah. You are going to help by asking some of the patrons to leave. You want to ask as few as possible to leave. You need to determine the size of the smallest set of characters as such that if all characters in S leave, all pairs of remaining characters can converse. So for example, in the first sample input below, blah, blah, blah. Okay, so we'll look at the sample input later. There are 100 people, up to 100 people, followed by n lines, each describing a character. Each of these lines starts with the name of the character, the language that they speak, and then a list of 0 to 20 languages the character understands but don't speak. All characters understand the language they speak. Okay, that's good. All character and language names in sequence of 1 to 15 letters, numbers, hyphens. Character names and languages separated by single spaces. Print a line of output giving the size of smaller sets of characters that should be asked to leave. So everybody else that left can reconverse. Okay, so let's try to look at this. So we have 7 people here. There's Jabba the Hutt. There's okay, so I'll just write Bib, and then Boba. There's Chewbacca. There's Luke. There is Grachogwa. I'll just put G here. I'm running out of space. R2-D2. Okay, what am I going to do? So Jabba the Hutt can speak Huttese and can understand Huttese. Who can speak Huttese? There's only one, Bib Fortuna. So I'm going to draw like this. I'm going to draw an edge in this direction. That means that if Bib Fortuna speaks, Jabba the Hutt can understand. Of course, everybody, if I want, they can draw an arrow like this, but I'm not going to bother with that. It's not too interesting that everybody can understand themselves. That's not so important. Okay, Bib Fortuna can speak Huttese. And who else can understand T's? So Bob, right? Because there's also T's here. Okay. So Bob Buffett can speak basic. Who can understand basic? This way. Chewbacca can understand basic. Luke can understand basic. I guess everybody can understand basic except Jabba the Hutt. Okay, I draw a graph like this. Chewbacca can speak this. And anybody else that knows, just, where's Chewbacca? What did I call it? So he can go this way. That's the only one that will understand. Luke can speak basic, so who can understand basic? Baba, Bib, and Chewbacca, G, and R2D2. Okay, and where am I? G can speak this. So who, the only one that understands, it's Chewbacca. And R2D2 can speak binary. And the only one that can understand binary is Luke. Okay, so hopefully I haven't messed up here in my
I think
drawing.
you
Did I
need
screw
an
up?
arrow between Jabba the Hutt and Bib because they both speak.
Did I not have? Oh, yeah,
Just
between.
a backwards arrow.
Okay,
And I think you also need one between Jabba the Hutt and Boba Fett.
Boba, that's because, oh yeah, yes, because he understands it. Okay, hopefully that's it. Okay, so now they said something about the first example. It says in the example, Chewbacca and Rachawa can converse because they understand each other, but nobody else understands this language, so they can't converse with others in the bar. So if they leave, everybody else can converse. So let's see what happens if we take them out of the equation. So we get rid of these two, Chewbacca and C. So we don't really care about any of these other arrows anymore. And then what they're saying is that everybody else can converse with each other. So what that means is that it doesn't matter which two people you pick from this remaining set, they can always talk to one another somehow. So for example, R2D2 can talk to Luke, of course, immediately. What about Bib? They can go talk to Luke, talk to Bib. And Bib can talk to R2D2 through Jabba the Hutt, Baba, and this way. It's not, the way that I draw is not the shortest way, but it doesn't really matter. And it turns out that every pair can communicate one way or another, directly or indirectly. Okay, so this is the question. You have to figure out the smallest set of people so that if you remove them all, then everybody else can communicate with each other. So the question I guess maybe we should ask is, in what situation can we do it without removing anybody? So what if the answer is 0? Okay, how can that be? Well, if I represent this as a graph, right, as I have a bunch of people, if everybody can communicate with each other, so then I pick any U and any V, there must be some way that I can go through this graph to go from U to V, and there must be some way to go from V to U. Doesn't have to be direct, it can be indirect. And this has to be true for every single pair. A graph, so if G is a graph, maybe I should use this. If G is a graph such that for all uv in V, I should say a directed graph, it's that there's a path from U to V and a path from V to U, then G is what we call a strongly connected graph. Okay, now, normally you would, maybe you only think about connected. What does that mean? In a normal graph where you have no direction, you have something like this. Here's a connected graph. That means between any two nodes, you can always travel from U to V. And it doesn't really matter what direction it is, because if you can travel from U to V, you can travel from V to U, because it's undirected. But when there are directions, something like this, in some way is still connected, but you can only go from U to V, but not V to U. So strongly connected means that you can go from anywhere to any other place, no matter which direction you consider, right? You can always follow the arrow somewhere. Or another way to say that is that there's always kind of like a cycle, okay? Because you were able to go from U to any other place and then back. Now, if you have a graph that's not strongly connected, you can also G, any graph G, any directed graph, can be partitioned into strongly connected components. What does that mean? It means that your graph, so let's say that you have a graph like this. 1, 2, 3, 4, 5, 6, and maybe you have something like 7 and 8. Okay, like that. This graph is not strongly connected because you cannot go from you cannot go from 8 to 3, for example. There's no way to go from 8 back to 3. But then maybe I should use a different color. If you just look at this part by itself, any pair of nodes in this part can get to each other because there's a cycle. So it doesn't matter which two you choose, there's always a way to go from one to the other. Similarly here and here, it doesn't have to be just cycle. You can have other things going on, but cycles are sort of the main features. They can be cycles and something else. So for example, maybe you have 9, 10, and 11, and then maybe something like this. Okay, so there's kind of cycles, although it's not just one single cycle. It could be like a bunch of cycles. In that case, all of this is one strongly connected component. Okay, so I'll erase that because it doesn't fit with my red circles. Okay, so, and what happened then is you can actually form a new graph if you want. That's what we call a condensed graph that consists only of connected components. If I call this connected components A, B, and C, then I can start from A, connect component A to B and C like this, meaning that there's a way for me to go from component A to B, component A to C, but there's no other way. There's no way for B to go to C and so on. And it turns out that if you do it like this, if you condense it, this graph is always a directed acyclic graph or DAG. There's no cycle. Because if there was a cycle, that means there's a way you can these would not be the largest strongly connected component. Okay, so why do we care? Why do we care is that if you have a strongly connected component, like here, and if you get rid of everybody else that's not in the component, then everybody in this group can talk to each other. And because any other nodes outside of a connected component, it's guaranteed to be acyclic because of this condensed graph. You cannot include anything that's not in your connected component, a strongly connected component. So if you want to include 4, for example, as one of the nodes that can converse with each other, the best you can do is cut all the things that are connected to you in the strongly connected component, and nobody else. And for every strongly connected component, you can play the same trick. You can say, well, I can kick everybody out other than 7 and 8, and then everybody out, and then 7 and 8 can converse with each other. So basically the idea is that you want to pick a strongly connected component and kick everybody out that's not that component. So how do you minimize the number of people you kick out? You find the maximum size strongly connected component because everybody else have to be kicked out. So this is a concept that maybe you have never heard of before, and that's okay because this is definitely something not that common, and I don't even know if this is something that courses in our undergraduate curriculum will cover. How do you actually compute this? It turns out that there are 2 different algorithms, but basically it's an application of depth first search, which if you have taken 3620 or are taking it, maybe you have seen it. But it really doesn't matter because if you recognize that this is what you want to do, and we talked about the code library. So code library here. And if you scroll down, there's strongly connected SCC here. So go to SCC. This is actually not my code, it's one of our alumni. And it tells you a set of nodes is strongly connected if for any pair of nodes in the set, there's a path from U to V and from V to U, and then blah, blah, blah. And so there's some code, so you have to make sure that the number of nodes you have is correct. Then you just copy this node. There's a graph data structure, and you call add edge every time you need to add an edge. And then there's this SCC. This is the main routine that you run. And then there's some comment that says you do not need to do this. You do not need this if you're only interested in the number of strongly connected components. What does that mean? Because this code also constructs this condensed graph that I talked about, and you can look at this to say how this works. But anyway, the idea is that I just took this code, and that's all I did. So how do I switch to the next? Here we are. No, hang on. No, that's the other solution. Okay, here it is. Okay, so so I guess I cheated because the code that I grabbed is actually from our World Finals library. That's a little bit more condensed, but it's still the same, more or less the same code. It's more condensed, there's fewer comments, but it's more or less the same code. So I basically read the input. So for each, there are 100 people, each person has a language that they speak, and then a vector of string that they understand, vector of language. So what do I do for each person? I read in the name, which I actually I don't think I actually even need the name. I figure out what they speak, and then I parse it to figure out all the language that they understand. And then I basically construct a graph for each. I look at all possible pairs of people. If they're the same person, I just don't worry about it. And then this is just a way to say that does the language that I speak, is it in the list of the language that J understands, basically, or if they speak the same language. If they, in other words, if whatever I speaks can be understood by J, I add an edge. And then I just run this algorithm that just returns the number of strongly connected components. And if the whole graph is strongly connected, then I'm done. That's the answer. Otherwise, I basically try to figure out how big each connected component is. And this code returns an array. Here it is, that for each vertex in the array, for each vertex in the graph, it will give a label, which is a component number. So the first component with 0, every vertex that belongs to component 0 has 0 in this array, and then 1 for the second component, and so on. And so I just collect them, basically. I just collect the component index and increment their appropriate size. Basically, I'm counting how many things are in each component. And then at the end, I just look for the maximum components and then subtract it from n, because the maximum component are the people that I keep, everybody else I throw away. So that's this way I subtract from n. Okay, so this problem, I would say the upper third of the contest in a regional contest, they should know this concept. And if they know this concept, they probably have this in the code library. And then if they know this concept and have this in the code library, then the problem is basically done. If you have never heard of this concept, you might still be able to come up with this, but probably unlikely to implement it in contest time. Okay, any comments, questions? Okay, now this one, so this problem A, it's a little bit of a tricky one, because if you know the concept, it's relatively easy, especially because you can just copy and paste the code and write a little bit of code. If you didn't know the concept, it's probably very difficult to come up with. Now, this next one, I would say it's one that even if you don't know the concept, there's some chance that you can come up with it. Okay, so what is the problem? Okay, maybe it's easiest to just look at the picture. You have a grid. Okay, you have a grid like this. Each grid location has a number. Okay, you're trying to move from the bottom left. So this is where you go into the maze, and you're trying to get out from the upper right. So always from the bottom left up to the bottom right. At each steps, you can do one of two things. You can move up or move right. One step. Okay, so for example, you can move this way and move this way, and maybe this way, this way. You can never backtrack. You can never move left. You can never move down. So here's one way, for example. And if you add up all the numbers that you see, so whatever it is, 9 plus 10, 19, 27, 37, 44, 52. So if I haven't screwed up, if I choose this path, the answer is 52. But if you choose a different path, you might get something smaller, right? So for example, if the first step, I don't go this way, but I go this way, then I would reduce it by 8 because I got rid of this one. Okay, so generally speaking, you want to find a path to go from the bottom left to the upper right with the smallest total cost. That's more or less what you need to do. But there's one more twist to it, which I won't talk about yet. But before we talk about the twist, do we know how to solve this problem? Right? Can we solve this problem if we didn't have the twist? Okay. And the idea is actually it's relatively simple. It's a dynamic programming problem. And you're going to say that f of xy, or row column, doesn't matter. Okay, let's use it, R, row and column. So xy, and it's always a little bit tricky because you have to decide which way is x and which way is y and what direction it goes. So I have row going this way and column going this way. So this location, it's r minus 1, 0, or capital R minus 1 and 0. And this is 0, c minus 1. Now I know that the problem says talk about x and y, and x and y is width and height. So if you want, you can use x and y. If sometimes some people like to use x and y, some people like to use row and column, but make sure that you know which one you're talking about, because in mathematics, most people use x and y in this direction. So if you use x and y as coordinates, you might get screwed up if you have to think about the y direction going upwards, because the indexing is kind of reversed. Anyway, it doesn't really matter. And also, if you use x and y, usually if you use a two-dimensional array, you have to be careful that you index with y first, because usually you index with the row index first. So anyway, I don't usually like x and y because of this. I usually try to change everything to row and column, just so that I don't get mixed up. But as long as you don't get mixed up, you can use x and y. You just have to be aware. Anyway, so I'm going to say FRC, it's equals to the minimum cost to get to exit, starting from the location RC. Okay. So that's what I'm trying to compute. What I want is to compute f of r minus 1, 0, because I'm starting from there. But it's a little bit hard to figure out. Okay, so let's call this array A. The easiest one to figure out is if I'm already at the exit, right? Because if I'm already at the exit, then the cost is exactly what's in the array, 8. There's really nothing to say. Otherwise, if I'm not already at the exits at some arbitrary R and C, the cost is whatever I'm on, because I cannot avoid it, but I can either go this way or go this way. So I would try both. If I go up, it would be this. Sorry, not A. It will be recursively, what is the best cost to start at this location and somehow end up at the exit. Or if I go right first, it will be this. It will be one of those two, because those are my only two choices. And whichever way I can get to the exit better, I would choose that way. So maybe this way is better, I don't know. So I would choose this way. And then recursively, this would say either try this way or try this way, and so on, and eventually get to here. So all you have to do is basically run this dynamic programming. And you can do it in different ways. You can compute this FRC starting at this location, this column, and move backwards. So every time you compute an entry, whatever you need, it's already computed. You can use it recursively, and then remember if you have computed something already or not. Okay, so that's one way of doing it. Are there any questions? Now, there's another way of doing it. That's, I guess, in some way equivalent. You can build a graph. Okay, just one node for every cell that you have. And we will draw an edge like this to all the places that you, if you're at that cell, where else you can go to. Oh, one more thing I forgot, I guess, there's a detail in the dynamic programming, that formula. I say that you can try going both ways, but it's possible that in some spots you can only go one way. Like at the top, you can't go up further because it's out of bounds. So if you get into that situation, then of course your code would have to be careful not to try to recurse in the direction that you can go. Okay, so we construct this graph, and the edge cost would basically be the cost to, so what is this? That this node is 1. So if I leave this node, I will have to pay, the cost is 1. This node has cost 0, so if I leave this node, it's 0. And this is 3, 7, 2, and 5, 8, 3, 7, 6, 9, 8, and so on. And then the last one, I'm going to make an artificial exit. And if you leave this node, it's 8. So what's going on is, if I decide to, let's say, choose this path, then I would go through this edge, this edge, this edge, all of these edges, and it will actually end up having the same. If I look at the cost on the edges of this path, it will end up being the same as the cost of this path based on the nodes that I hit. So I can construct this graph. And now that I've constructed this graph, I can basically run any shortest path algorithm that starts from here all the way to the exit and ask what is the shortest path. And in this case, the easiest algorithm, I guess, would be Dijkstra, which again is in the code library, okay? So the Dijkstra's algorithm will give you the shortest path and the shortest distance. You actually don't care about the path, you just care about the distance, and whatever the distance returns is the answer. So that's a different way of doing the same thing. Okay, any questions about this? But that's not the problem. That's not the problem, because the problem has a little bit of a twist. So where's the twist? The problem is, the twist is that he remembers that he has a cryptic code key that he found while searching the layer, and he reaches into the pockets and removes a paper with a large integer on it, each of whose digits is in the range of 1 to 9. So you have a long string of 1 to 9. Okay, so 1, 2, I don't know, 3, 4, 9, 1, 3, whatever. You have a long string. Okay, what can you do with this? His training kicks in again, and he remembers the way this works. Whenever he wishes, he may use the leading digit of the key, which permits him to hop over that many squares. Again, you can only hop in either up or to the right. Whenever he uses the leading digit, it is removed from the number. So when you're down here, you can go this way by 1 step. You can go this way by 1 step. But you can also decide to get rid of this first digit and hop 1 step this way and hop 1 step this way. And once you decide to hop, you cannot use this one again. And the next time if you want to hop, you have to hop 2 like this. Okay. If you decide just to move 1 step, then you don't use up this digit and you can save the 1 for later. So it says that if your magic key is 1, 2, then you can first start from here move to here, then hop up. Okay, so the first, his best path is to step right, hop up, and then hop right, because the first time you can hop one step and the second time you can hop 2 steps. Step right, step up, and that's supposed to be 18. Is that right? Yeah, 18. Okay, so now it's not just that you can move left and right, right and up, but you can also hop. But if you decide to hop, you will use that up. So this time now, your F, R, and C, your dynamic program is not just about where you are, because you also have to worry about what is the code string that you have left. Because if you have more code string that you have left, then you can do more, you can do different things. So what is it? So maybe you have a letter number K, and this is the number of code key digits used so far. Okay, so you start, originally you want to compute, again, F of R minus 1, 0, and 0 at the beginning, you don't have any digits used. And then the end, you have F of 0, C minus 1, sorry. And then any K, it's equals to the array content. Okay, it doesn't matter how many, if you're at the end, it doesn't matter how many digits you have used so far, it's always going to be that. Okay. And then the question is, how do you deal with the rest of this? So let me just erase everything. Okay, so F of RCK equals to the minimum cost path starting from RC and using K digit from key. And let's say that the key length is, what do I call it? Length. Okay, so we want F of R minus 1, 0, and then 0, because at the beginning we haven't used any key yet. So base case, F of 0, C minus 1, K, it's equals to whatever contents it's at that location in the original array, and that's for all K equal to 0, 1, all the way up to length. It doesn't matter how many code digits you have used. If you get there, that's always the cost. Okay, and then generally, F of RCK, it's equals to what? Okay, so you can decide not to hop. So you can hit ARC plus minimum of F of R minus 1 CK, or F of R C plus 1 K. So we are not using any, we're not using any digits. So we're not using any digits, so recursively we still have used the same number of digits. Okay, so this means, the first line means no hopping. Okay, what about hopping? If you decide to hop, it'll be a this plus min of f of r minus what? Okay, so r minus what? That would be actually the size of the hop. So I'll just say hop bracket k or something like that. I'll explain what that means. Or okay, so if my hopping, this is my key. So my key is equals to, it's a hop. I guess I should use the word. Okay, why don't I just change it to say key instead of hop? That's probably better. So my key, it's going to be a string of a certain length. 1, 2, 1, 3, 4, 7, whatever. Okay, so this is a 0 position, 1, 2, 3, 4, 5. So if I have used 0 so far, if I've used 0 digits so far, then the next hop to consider is key bracket 0, which is this one. Okay, and basically this hops over by one step. Okay, and this hop over, if I'm looking at 1, 2, then it hops over by 2 steps and so on. So I know that I'm kind of abusing the data type here, because if this is really a string, then these are characters, so I can't really do this properly. So let's say that I'm just pretending that these are integers. I'm completely abusing data types here, but you can easily change these to integers if you want. And then basically, if I decide to hop, then the next, when I recurse, I have to know that I have used up one more digit for my key than before. And of course, I take the minimum of all these two branches. So altogether, there are 4 things to consider. This one, this one, this one, or this one. Take the minimum and add to AR bracket C, and that's the answer. With the caveat, there are a number of caveats. First of all, these indices here have to be in bounds, right? If you try to move up or down or hop up or down, up or right, and it goes out of bounds, then of course you cannot use that one. Also, this k plus 1 here, it's possible that you go out of bounds, because it may be that you get to here saying that you have already used up all 6 numbers. And then you're trying to look at key bracket 6, and of course it's out of bounds. So if that's out of bounds, then of course you also don't consider these 2 branches, right? So there's a little bit of implementation detail here that you only take the one that makes sense. But there are potentially 4 different ways you can go, 2 directions, and each direction you can either go 1 step or hop, right? And then you remove all the ones that don't make sense, pick the minimum, and then you can run this dynamic programming. And because they tell you that there are most 50 digits here, that most 100 rows and columns, the total number of states that you have to know, it's 50 times 100 squared, which is not that much, right? So this is 50 followed by 2 zeros like this, 500,000. So that's really nothing. Now, if you want, you can also set this up as a graph in a similar way, except that your graph nodes would not just be 1 node for every cell that you have, but kind of 51 nodes for every cell, because every cell you have to say, well, what if you got here having used 0 letter from the 0 digit from the key, 1 digit from the key, 2, 3, 4, all the way up to the end, using all of them. And then you can set up the same Dijkstra graph if you want, and you can run Dijkstra. So you can do it either way. I decided to try Dijkstra. Where's my solution? Here it is. So, okay, so the first part of the code, really there's not much going on other than pasting the Dijkstra's algorithm that you find. This is Dijkstra, we call it Dijkstra sparse in the code library for graphs that are not very dense. So this graph, each node only has basically 4 edges. So it's pretty sparse. And so all of this is just Dijkstra code. And then I have to have a way that, given the row and column and how many key digits you have used, convert it to a number, because my graph code assumes that every node it's between 0 and n-1. That's the node index. And this whole part is just setting up the graph. So basically, for every node, I double loop all the cells. And then here, I basically, for each key length, for each of the 2 directions, I'm using this, you see, I'm using this direction trick, look up and look right. This is the destination if I look up and or look right, whichever way it is. If it is inbound, then I add an edge. And then I make sure that I haven't used all of the digits. And this basically just figure out where I would end up if I skip. And then I add an edge if it's inbound. So it's a little bit complicated, but basically I set up this graph. And then finally, all I do is I just call Dijkstra. And once I call Dijkstra, I basically ask what is the distance from the start? So the start is this, to the end. The end is this location, but I don't actually care how many of those digits I have used, so I try them all. So I try with no digits used, 1 digit, 2 digit, all the way to all digits used. And for each one, I will have a distance, and I just take the minimum over all of them. And then the way that I construct this graph, I did not take into account the last node, so I just add the last node. Because the way that I construct this graph, I always, basically my edges are always the containing the cost of the node that I'm exiting. So when I get to the end, I haven't exited anything yet, so I need to take care of that. If I want to, I can actually add an extra node at the end and have the final location sent to that, but it doesn't really matter. So anyway, there are multiple ways of doing this, but I think the most important thing that I want to point out is when you have a grid, especially if you can only go in 2 directions, up and to the right, the important thing to realize is that there's no way you can ever repeat a cell, right? So you can't go from here, then here, and then here, and maybe here, and back to here, and revisit this node. There are no cycles because every step you can only move to up or to the right, right? There's no way you can actually form a cycle. And when you have that, then you should think about dynamic programming, recursion, or recursive thinking, and so on. And then if you have recursion, you can think about, well, can I remember some of the things I compute so I don't recompute the same thing over and over again, right? So for example, here, maybe I want to know what is the best way to go from here all the way to here somehow, but I can come this way and ask this question. Maybe I come this way and ask this question, because in both of these ways, I end up here. And if I end up here, I want to recursively ask what is the best way to get here. if I don't remember the first time, if I don't remember that I've computed the answer and stored, then of course the second time coming here, I would recompute. And the third time, because I could come here this way, and maybe I can come here this way. There are many ways I can come here. And if I don't remember that I've already seen this and computed this once, I might just compute it over and over again. And that's not good. And the key thing is to realize that you can remember. The first time you see something, remember that you have seen it and store it, so that the next time you see it again, you just look it up and don't bother recomputing. And that's dynamic programming. So this one is also relatively standard for, I would say, again, the top third of the team in the teams in the region. I think that should be relatively straightforward for those teams. If you're new, of course, it is not straightforward. But if you can try a little, maybe if you can try this and try to do that, then maybe maybe with some practice you'll get this type of problems. Okay, so if I go back to look at the problem set, those are the 5 problems that our top team managed to solve in the actual contest. And the top team from our region, the only other problem that they solve is E. Nobody tried B and nobody tried G. Well, I guess one of our teams tried G, but it turns out that it's much harder than it turns out to be the hardest problem in set, I think. And part of the issue, I think, was that maybe the person that was doing the problem didn't read the problem carefully to know what it was actually asked. Basically, the problem says that you have a bunch of buildings. Maybe it's easier if I just draw the picture. So let me draw a picture. So you have a bunch of buildings side by side. So I'll just draw them like sticks like these. Oops. Okay, try again. You have a bunch of these buildings. Some are taller, some are shorter. But everybody is kind of jealous of everybody else, jealous of the neighbors. So, for example, this one here, if you look across, if you look at the neighbors, if you look at the average is here. So let's just stick to the average for now. And this building says that he's not as tall as the average of the neighbor. So I don't like that. So I'm going to build myself up so that it hits the average. This one is the same. So I've got to build myself up and so on. And maybe this one, I don't remember what happens to the ones on the edge, but let's imagine that this sticks. But the thing is that it's possible that after you finish building up, you're not done yet. So let's try to do this. Okay, so let's say you have this situation. If I look here, this building wants to go up, this building wants to go up, but this one is fine because the average of its neighbors, right? It's maybe it's right, maybe you're right on the average. You're not shorter than it. So this one doesn't need to build up. Okay, so you build this one up to the average of the 2, and then you build this one up to the average. But now, you know, this used to be here. So if you draw a straight line from here to here, the average is here. So but when you build this one up, this is no longer, the average is actually higher. So this one actually wants to build up to the new average all the way here. But now this one, you see, the average with this one is now here. So this one wants to move up and so on. And it might not be done in just one round. There might be multiple rounds. where everybody people that wants to go up, they go up to the average of the neighbors, and then that affects some other buildings that have to go up, and the buildings keep going up. The one thing that's maybe, I don't know if it's clear or not, is that eventually this process will stop. It will converge, and then nobody moves anymore. And the question, I believe, was the height of the tallest building. Yeah, print the height of the tallest house after all houses have been remodeled over infinitely many days of the process described above. Okay, so I think, I'm not going to describe the solution, but I think what the attempt was from one of our people is that they didn't realize that you can keep going up afterwards. So I think the solution that was submitted was simply go through each building and decide whether they need to increase the height, increase them once. So do it from left to right in one scan, and that's it. But every time a building changes, there might be more buildings that needs to be updated. And it turns out to be a very mathematical problem. It involves parabolas and so on and so forth. And I'm not even going to say much more about it. Anyway. But I think the most important thing, so unfortunately, the one of unfortunate thing for this contest was that the scoreboard was limited only for our own university. It's not easy to see the global scoreboard unless you cheat and go to the open contests for the people that are not even eligible to compete. So you couldn't see that there are not many people solving this problem. So in a real contest, you would be able to see which problems are popular, which problems have lots of solutions, and which problems don't have any solutions after a while, and then you would know that those are the ones that are hard, right? Anyway, so, okay, I'm going to stop here. I guess for the team one, I will maybe chat with you in the other Discord group to talk about how problem E is solved and how problem B and then maybe H, no, not H, the G, the skyline. But I think B is actually not as hard as, conceptually it's not hard, but I think coding is absolutely horrible. But E, it turns out to be really easy to code if you get the right algorithm. So we'll talk about that separately. So, okay, so what, oh, wait, I stopped the sharing. I want to keep sharing. So what do I want to do? I want to, for the not advanced people, most of you have probably not seen the last year's regional, or last year would be 2 years ago now. So it's rmc19.caddis.com. This is the regional contest from our region last time. Okay. And you can look at the standings, right? So here we are. Our team one was 5th, and they solved 8 problems. The top team from last year's the winner solved 9 problems, and you can see. Just a minute. Sorry, I can't mute the dog. So you can see from here that there's some problems that are not so difficult based on number of teams solving it. Right, 71 teams out of 81 teams solved it for the first problem, and then some are a little bit harder, right? 67 teams. This is also the other easy one, and then 43 solving D and I, and then D 29 solving, and then some of these other ones have fewer people solving it. Okay, so what I would like to do is, if you look at the scoreboard, right, there are 72 teams, although I'm not so sure that these two teams really showed up or not. So if you are 72, let's say 70 teams, so basically somewhere between 25 to 50 would be the middle third. And you look at 25 to 50, so at the top end, you need to solve 5 problems. The bottom end of the middle third, you need to solve 3 problems. Right? So if you can solve 3 or 4 problems quickly, you would be easily in the top half if you can solve 4 problems quickly, right? And then only, so, you know, you don't have to solve the hardest problem. Of course, you want to avoid getting trapped by the hardest problem, but you don't have to solve the hardest problem to do reasonably well. I mean, you won't be able to be top 8, which is the number of teams that get that advance to the next stage. But even if you solve the easy problems quickly, so piece of cake, loss lineup, tie Terry, integer division, and if you can solve one more, you are well in the top third of the contest, right? So what I want to do, especially for those of you that are starting out the first time, let's try to aim for, you know, getting the easy problems, but accurately and quickly and correctly, right? So for example, our team, this second team, they solved 5 problems, not as quick as some of the other ones, right? If they solve 5 problems really quick, that's already 12 spots, right? So there's a big spread, 5 problems, and they're not, the problems themselves are not that hard, I hope. But what I want to do is I want you to look at these 5 problems, A, B, T, I, K, and what else? B. Those are the 5 easy problems of this set, and we'll talk about it. We'll talk about it. Try to do them. So you can go to this rmc19.caddis.com. You can click on this. You won't be able to, when you try to submit, it won't let you show up on the scoreboard, of course, but it will still tell you if you got it right or wrong. And try to do them quickly. And then see how many times it takes you to do. Okay. I guess that's really all I want to say. And for team 1, I guess I will tell you something else in the Discord chat. Sounds good?